Hi everyone, and welcome to this session, which will be about parametric cold-formed sections in Advanced Design 2023. So parametric means that they can be defined by the user, and together we will first recall the basics of EuroCode 3 Part 1.3. Then we will do an example on a hat section that you may also call omega section. It will be a beam element, a girder exactly, so it will be a member subjected to compression and bending. And then we will do another example on a different section. It will be a sigma section this time, acting as a purlin, so it will be a member in mostly bending, but with the contribution from the roof. So let's start with the basics. So cold-formed design is covered by EuroCode 3 Part 1.3, but it will reuse some concepts that were introduced in Part 1.5. And Part 1.5, you probably already know about that. It's used for usual Class 4 design to identify the ineffective parts of a section. And all the formula there, all the concepts, they will still stand for cold-formed design. So here you get a sample of the common cold-formed sections you might have in building practice. You see we have a lipped channel there, we have a Z section and a sigma section, which are often used as purlins or side rails. We have angle sections, you have a channel with ellipse, a Z section, and then the hat section that we will use for our first example. And now all these sections can be defined by the user in advanced design. You can see them in the drop-down list. You have the hat section, sigma and Z, the C, but let me show you that directly in advanced design. So I will open the advanced design program. We will start a blank project, and when you select a linear element, see, you will be able to, well, first you will select a steel grade, so it would usually go for a high one like a 355 or 350, and you will, in the properties, like select a parametric, a user-defined section, and you will find at the end of the list, well, the omega section. You can see right away how it is displayed in the the 3D rendering. So you will have as well like the sigma section, and then you will have some subtypes, because you can have a sigma section with straight leaps or with inclined leaps, or an asymmetric one. And then you will have a Z section, same with inclined leaps or straight leaps. You will have the channel, so the lipped channel, the one with the asymmetric channel with a leaps, and the same with a leaps. You can have the angle section, so you can make it symmetric or not, because you have access to the height and the width. And you also have the zeta section. And when you define a section there, the characteristics are computed on the fly. You can access them from the manager. See, and when you pick like the hat section, you can display the properties. So you will find there like the gross area, the inertia, the IY, IZ, you get the torsional inertia, the warping constant, the elastic bending modulus, about Y, about Z for top and bottom, left and right. You got the plastic one, not sure they have any use anyway, because most section, the cold-formed section, will be elastic, like class 4, class 3. Yeah. So you have now this section available right away, and of course you also have like other sections available from the library. Alright, so let's get back to the basics. So the main difference between a call form section and like let's say the usual one would be the thickness. A call form section will usually be very thin. So if we compare a call formed channel with an equivalent UPN, you can see the call form one is way thinner. It's only 2 millimeters. There will be usually 1 millimeter, 2, 3, so very thin sections. But even though they are very thin, they are still strong and stiff enough to sustain the loads. And what makes them strong is actually the multiple bends they have along their sections. You see, they have multiple foldings, multiple bends, and this is what makes them stiff. It's like when you have a piece of paper, you see it's very thin, you cannot do much with it. But if you start folding it, if you start bending it, it will make it stronger to the point where you can make objects with it, you can make a paper plane, and it's the same with all materials, for paper, for plastic, and of course for steel. The more you bend a section, the stronger it gets. So to qualify as a call formed section, you have some geometrical proportions to meet, and it's mostly about the width to thickness ratios. And the complexity of call formed design is because you have two effects affecting these sections. The first one we already know, it's called local plate buckling, and it's covered in part 1.5, and it's what is causing some parts of a section to become ineffective. You see, in part 1.5 you have two sets of tables. One is for the internal compression elements, so that would be the web and the flanges, and you have different tables for the outstand compression elements, and that would be the hanging parts, typically the lips. So you're supposed to use this table to pick the right table with the right stress distribution, to compute a buckling factor, and to find out the effective width of each component. And because of local plate buckling, see, you will lose some parts of the section that are in compression. Like you will lose maybe some part in the middle of the flanges, some part in the middle of the web. You will lose some part at the end of the lip. You see, so this would be the effective section in pure compression. So that's local plate buckling. It's nothing new, and it still applies. But then you've got another effect coming in, and this one is specific to call formed sections. It's called distortional buckling, and it is causing the end stiffener of a section. The end stiffener is the lip and half of the compressed flange, and it is causing this end stiffener to get a reduced thickness. And you have to properly assess the reduced thickness. You see, when the whole section will be maybe 2 millimeter, probably the end stiffener will only be 110 or 120. So it doesn't seem like much, but it can make a huge difference on the design. And when you combine these two effects, local plate buckling and distortional buckling, you get the section that you're supposed to use for the design, and it can be really different from the initial section, from the gross section you started with. See here, if we consider a Z section, you've got the gross section initially, but in case of pure compression, well, as we said earlier, you will lose a good portion of the web, which is entirely compressed. Same goes with the flanges. You will lose the middle of the flange, top and bottom, because they are both compressed. You will lose a small end probably on the lip there, and the end stiffener will get a reduced thickness. So this is a effective section, but only in pure compression, because then you have to consider um, like these effects will differ in case of pure bending, because the stress distribution on the section will be different. See, only the top of the section, for example, will be compressed, so the ineffective parts will be on the top flange, at the end of the compressed lip, and near the top of the web, because the bottom of the web will be in tension, so it will be untouched. And same goes with the bottom flange. The flange is in tension, will not be affected, and neither will the stiffener in tension. And the reduced thickness will only apply to the compressed end stiffener. And believe me, in cold form design, just finding out this effective cross-section and the effective characteristics that go with them is actually like 50% of the work. It's very tedious, you can easily mess up, it's really complex, and you have to do it for pure compression, for pure bending, in strong axis and a weak axis, with compression on the top flange, compression on the bottom flange, compression on the left, on the right. So yeah, just for that you really want a software to do that for you. But once you got these effective characteristics, then you can perform the design checks, and some of these checks are really basic and straightforward, like you see in pure tension, pure compression, shear force. There's nothing too complex about it. You're given a formula and you compare the design force, the design internal force, with the resisting force. But when you start combining the internal forces, the formulas can get a bit more complex. You can see here when we have a mix of compression and bending, well, you have some additional moments that you have to consider in the design, and these additional moments, the delta my and delta mz, they are due to the shift of the centroid of the section. Because as we said, you start with a gross section, but the section you consider for design is the effective one, and because you lost some part of the section, it's causing a new position of the centroid of the section. So the axial force that is applied initially is now applied with an offset to the centroid, and this offset will bring you some additional moments. It can be a moment about Y or about Z or about both, depending on how the centroid of the section is drifting. So these extra moments also have to be considered in the design. And then you have the really complex checks, the ones that would involve the buckling effects and lateral torsional buckling ones. And by that, by buckling, I mean flexural buckling, like strong axis, weak axis, but also torsional buckling and torsional flexural buckling. Like, you got them all. And it will also involve the lateral torsional buckling that will affect the bending resistance. And now we will actually apply that on an example. See, we will see how the effective characteristics and the effective sections are found out by advanced design, and how the design checks are performed. So for that we'll consider a hat section acting as a girder in an advanced design model. Alright, so this is the structure we will be working on. So as you can see, it involves a lattice girder, and what I will do is I will turn the top chord of this lattice girder into a cold form section. So I will first select a higher grade, see usually in the 350 or 355, and then I will select a user hat section from the list. So Omega section there. Yeah, it's default section, quite okay. I got a 180 for the height. I can make the width 365, 175 for the top flange. I can increase the radius, and I will keep a 3mm thickness, and I will go with that. And at this point we can just run a finite element calculation to check the internal forces that we get in there. So the model is computing. We will get of course the displacements, but I'm interested in the internal forces in this top chord. So what I can do is work on a specific part of the model right there, and I will select this part of the top chord, and I will check the actual force to begin with. And as we could expect, because I'm working on the top chord, it is compressed. The bottom chord would be tension, but here I'm getting significant compression, because in advanced design a negative actual force stands for compression. So significant compression and probably a bit of bending moment. It's not huge, but it will impact the design. So because I have compression and bending, I can expect the critical check to be about compression plus bending with the buckling effects and the lateral torsional buckling effects. And in order to help with these checks, what I can do is define some restraints to help with the out of plane buckling and with the to prevent the twist of the section. And to do that with a call form section, you would actually go, that would be something you define in the advanced stability dialog. See, so first you need to ensure that the advanced stability is activated, and then you will open the advanced stability dialog to define additional restraints if needed. For example, here advanced design automatically detected 3 supports. You've got one at each end, so beginning and end, and it also detected the connection with the purlin. And let's say you have a braced purlin that you want to take into account to help with as an out-of-plane support. You can do that because this support can be defined as a TY restraint. See, it will be TY fixed, it will be a support in the weak direction, preventing the out-of-plane displacement. But here we would also like to define some 1, 2, and 3 rotational restraints between each vertical to help and to prevent the lateral torsional buckling effects. So you can do that because you can define some additional restraints that are not featured on the global model. So you just go there, you add one, so at 1/4, so that would be 0.79, and you would define it as fully free except for the torsion restraint. Then you would define the purlin as acting also for preventing the torsion, and you can place one more at, that would be 237, same with fully free except for the torsional restraint, and you see you've defined all the potential intermediate restraints. Of course, we could have defined a discrete restraint all along the member in a linear manner. In the bedding tab, then you will define the initial imperfection, and the load application point. And with that, well, we're all set, and we can immediately run the steel design calculation on this critical segment there and check the results right away. So in the shape sheet, you see we've got all various checks that were performed. We got the pure compression, so this is the design force compared with the axial resistance with the effective cross-sectional area. You've got the bending in both directions, got the combination of both bending, but of course, as we could expect, the critical check will be about bending and axial compression with the buckling effects. And that means the buckling affecting the axial resistance and the lateral torsional buckling affecting the bending resistance. We can get more information in the detailed version of the shape sheet with here the critical check. So we get the formula and we get the article reference 625. And if we go back to our presentation, see that that is indeed a critical check where bending and axial compression both come in, and this is a complex check because you have to consider the effective cross-sectional area with the buckling effect and the effective bending modulus on the flange that is subjected to lateral torsional buckling. So to do that, advanced design first of all will find out the effective characteristics. That means the effective cross-sectional area in pure compression and the effective modulus in pure bending. Then it will identify the design forces. That means the design axial force and the design moment with the potential additional moment coming from the shift of the centroid. And then it will compute the buckling factor. So buckling for the axial resistance, compression resistance, and the lateral torsional buckling coefficient affecting the bending resistance. So initially I had in mind to take you through the whole workflow for the effective characteristics, but I pretty quickly realized how long it would take. So I will go quickly over the slides, and you will be able maybe to pause the recording if it's ever made available. You will be able to pause the video if you want to, if you're interested in this part. But the idea is, first of all, you will not deal with the overall dimensions, but with the dimensions to the midlines. You will also consider not the nominal thickness, but the core thickness, where you subtract the thin layer of metallic coating, which is usually 0.04 millimeters. And then you can apply the first effect. See, local plate buckling, that means the ineffective width, starting with the top flange, which is in pure compression, where you pick the right table, you compute the buckling factor, and in the end you get the effective width on the top flange. So you get 56 on each side, so you're losing the middle of the top flange, you're losing a good third of the top flange. Then you can proceed to the left and right plates, so still in pure compression, because we are looking for the effective cross-sectional area in pure compression. So you identify the right table, internal compression elements, the right stress distribution, and you find out the effective width on top and bottom, so left and right. And finally you can work on the leaps, left and right. So this time it is an outstand compression element in pure compression still, and you find out the effective width because you're losing the very end. And this is how you end up with the effective cross-sectional area after the effect of local plate buckling. But remember, there is a second effect coming in, which is distortional buckling, and it's affecting the end stiffeners, left and right. And the idea here is to find out the reduced thickness. See, and for that, well, first of all, you need to compute the new effective length of the hanging part, then that will give you the cross-sectional area of the end stiffener. You will also identify the neutral axis position of this system in order to compute the inertia of the end stiffener, of the effective end stiffener. You will also compute the stiffness of a fictive spring placed here, and that will give you in the end the reduced thickness. So very briefly, you see we compute a buckling factor that will give us an effectiveness ratio for the end stiffener, which in turn give you the effective length of the hanging part. Knowing the effective length, you can compute the effective cross-sectional area for the edge stiffener. Knowing that, you can find out the position of the neutral axis, so that would be the B1 and C1 distances. Knowing the neutral axis position, you can compute the inertia of the edge stiffener. You can also compute with the formula from the record 3 the stiffness of the fictive spring that is placed there. And with all these intermediate values, see the stiffness of the fictive spring, the inertia of the edge stiffener, and the effective cross-sectional area, you can compute the anelastic critical buckling stress in the edge stiffener, which in turn lets you find out the relative slenderness of the stiffener, which will give you the reduction factor to apply on the initial stiffness to get the reduced thickness. You see, with all that, we go from a almost 3 millimeter thickness down to a 208 millimeter. So we are losing an entire millimeter there. So it's significant, and that is why in the record 3 you are allowed and to perform some optional but welcome iterations to mitigate the thickness reduction. So the idea is to go back to the beginning to perform, to re-inject the final results until the thickness stabilizes. You see, you get a new thickness, a new reduction factor that you will inject at the beginning, and you perform iterations until the reduction factor stays the same. So here it took me like 9 iterations, and that way I could like go from a very 2.1 reduced thickness up to a 2.3 thickness. So I limited the thickness reduction with these iterations. So Advanced Design does these iterations. It does like a bit less, because else the calculation would take too long for each member. But you see, it goes from instead of a 208 millimeter, we managed to increase it to 223 millimeter. And with all these effects, like once you get the ineffective parts, the reduced thickness in pure compression, you get the effective cross-sectional area to be taken into account in the calculation. And remember that because you've got a change in the section, because you're losing some parts, ineffective parts, and the reduced thickness, this is causing a shift of the centroid of the section. So the axial force is now applied with an offset, and this offset, this shift of the centroid combined with the axial force, is bringing you an additional moment that must be considered in the calculation. But this was only for the effective cross-sectional area in pure compression. Remember that the member is subjected to bending as well, so you have to find out the effective bending modulus, applying the same workflow with different formulas. So of course I will not repeat this process, it would be like unbearable. So I will just go straight away to the effective cross-section in pure bending as they were found out by Advanced Design. See, in pure bending, you have to consider two outcomes. You've got pure bending with compression on the top flange, and you've got pure bending with compression on the bottom of the section. See, at the top flange, you've got the ineffective part there, but the rest is untouched. Whereas for compression at the bottom, you've got the ineffective part there and the reduced thickness. But remember that for the critical location, we've got a negative moment, and given the conventions of advanced design, that means we've got compression on the top flange. So we can assume that the effective characteristics we will need are actually the one bringing compression on the top flange. But anyway, to be completely safe, advanced design will also check the tension part of the section with the other value of the effective modulus. Anyway, once you get all that, well, you can compute the buckling factors. So for buckling, there will be 4 of them, because you've got flexural buckling in both directions, about Y and about Z. Then you've got torsional buckling, and then you've got torsional flexural buckling. And for each of them, each 4 of them, you've got to compute a relative slenderness, then a phi factor, which will involve an alpha parameter. And important information, this alpha parameter depends on the buckling curve you consider. But as you can see, the hat section is nowhere to be found in this table. See, we've got channels, we've got Z sections, angles, but the hat section is not featured. So at first I thought we were supposed to go with curve C, as in other cross sections, but we asked around, and turns out for a hat section you can go with curve B, which is better because you've got the alpha parameter is in fact smaller. It's 0.34 instead of 0.49 for curve C. And we also learned that there seems to be a new version of the Eurocode 3 on its way, and this version is should feature the hat section in this table. So you compute a phi factor, and from the phi factor you get the Xi coefficient, the Xi buckling coefficient. Actually you get 4 of them, you get 1 for each, and you're supposed to retain the minimum, because that will be the first critical buckling mode you would reach. So what advanced design does for buckling is that during the advanced stability calculation, it will find out the amount of load that is causing a numerical instability. That means you've got a potential failure of the member. Here we got a 13 something critical load. That's the information you get in the critical load factor section of the shape sheet right there. Critical load factor, you can see we got here I got 1383. That means for 13 times 83 the design forces, I would get a failure, the first failure of the member, the first numerical instability. That means the critical axial force is in fact given by 13 times 83 multiply the design axial force, which was about 166. That gives me a 2.3 meganewton critical force, which is the value we get right there for n. This is the first critical n that will be reached by the member. And knowing this critical n, advanced design can compute the buckling factors to get the buckling resistance. Right there. So this was only for buckling, because when it comes to, you see, the member is subjected to bending as well, so that will involve finding out the critical moment. And again, we will use the critical load factor, because that means we've got the critical moment will be 13 times something times the design moment. which gives us an 86 critical moment. And we can compare it with the initial design moment, and because the design moment is way smaller than the critical moment, see the ratio is only 7%, and because it is below the limit of 16%, in this case you are allowed to, you can safely ignore the lateral torsional buckling effects. It is stated in the Eurocode 3, the general text, where the ratio is below lambda LT0 is 0.4, so that's why you get 0.16. You can ignore the LTB effects. So of course, depending on your local annex, the limit might be different. For example, in France it is 0.2 and 0.04, but here we got no lateral torsional buckling effects to consider. When we've got all that, we can perform the critical check, bending and axial compression, because we've got the axial force, 165 something. We've got the design moment with the additional moment from the shift of the centroid. We've got the buckling, the axial compression resistance with the buckling factor, the effective cross-sectional area, and the yield strength, and we've got the buckling, the bending moment resistance with the buckling factor, the lateral torsional buckling factor, which is 1 because the effects are neglected, and that gives us the design work ratio of 95%, which is in line with the 93% I got from advanced design, because advanced design is actually more accurate than I am in my hand calculation. Alright, so we've got a few minutes left, so we can move on to another example. This time we will consider a sigma section acting as a purlin. It will be a sigma purlin on a two-span sigma section on a two-span purlin. And yeah, in the Eurocode 3 chapter 10 for purlin design, you can either apply the analytical method from chapter 10, or you can go with a numerical method if you got a software for that, where you will introduce the rotational spring stiffness of the roof, and you will also introduce an initial bow imperfection along the member, which will be based on the critical buckling mode that you find by a model analysis. And this is what advanced design will do through the advanced stability feature that we have. Alright, so this is a model. We have purlins. I will just make sure that they are defined as user sections, sigma sections. Alright, and we'll first run a finite element calculation to see what kind of internal forces we are dealing with. So here I should get some significant in-plane bending moment there, but no axial force. So bending moment, do I have it? Yeah, alright. So yeah, it's a two-span purlin that we will design. But to design a purlin, you are allowed and you are advised to introduce the stabilization you will get from the roof, because the roof can stabilize a member, providing a torsional restraint, and we will do that in the advanced stability dialog again. So make sure advanced stability is enabled, and we will define, so first we will define the nodal supports we might have. You see, because here advanced design has detected 3 potential supports. You got the beginning and the end of the purlin that I will define as a hinged right there, beginning and the end. The middle support is also hinged because the purlin is hinged on the supporting rafter. But then you can introduce additional point restraints, like let's say you have anti-sag bars in the middle of each span. Well, you will introduce them. The first one would be at 225, middle of the first span. It will be a TY restraint. So restraint the weak axis, preventing the out-of-plane displacement. And you will add another one for the second span at 675 with acting in the Y direction. Okay, so this is for punctual point restraints. But then in the bedding tab you will be able to introduce the roof stiffness. See? So you will place it on the top flange and it will be a torsional stiffness, a torsional restraint. And you can compute that based on the number of connectors per meter of purlin. See, if you have 5 connectors per meter of purlin, there is a formula in Zero Code 3 where you take the number of connectors you have per meter, so 5, you multiply it by 130 and you get the rotational stiffness from the roof. So 0, it is in Newton meter, so here, because I'm in kilonewton meter, it will be 0.65 on the top flange. You can also introduce a shear field if you computed it. Then you will introduce the initial bow imperfection based on an eigenmode and an eigenvector analysis. You will decide on the application point. It can be on the top left if you're dealing with only gravity load, or top center if you've got uplift as well. And the farther away you are from the shear center, the more torsion you will get. And when you're done, you can safely run the steel design analysis on the member, on this purlin, and check the results. And for purlin, after an advanced stability analysis, the design check you will be interested in is actually the total direct stress, because it will involve like you've got the in-plane bending moment amplified with the potential second order effects. You've got maybe a small out-of-plane moment, but most of all you've got the torsional and warping effects, which are compared to the limit stress based on the average yield stress, FYA, which is it's not 355, it's an amplification due to the bends you have on the section. So here the member is definitely okay. If we get back to our slides, you can see that for any check involving torsion you are allowed to consider the average yield strength, which is a bit more favorable. And as you can see, defined in chapter 10, we've introduced the rotational spring restraint provided by the roof. We've decided on the application point for gravity load, and it's a bit more unfavorable for an uplift load because it's farther away from the shear center, and you can also introduce the shear stiffness if you've computed it. Alright, so that's it for this session. So brief recall of what we've seen. We've mentioned the basics of Euro Code 3 Part 1.3 with local plate buckling and distortional buckling. We've applied all that first on a hat section where we found out the effective characteristics. We identified the design forces with the additional moments from the shift of a centroid, and we've computed the buckling and lateral torsional buckling factors to get the final work ratio. And then we've moved on to a sigma section example where we've introduced the stabilization we could get from the roof sheeting. Alright, so I'd like to thank you all for your attention, and I hope I kept you interested. And if you have any question, you can ask me by email, or you can ask me right now, because I will be hanging for a few more minutes to answer any question you might have.